Since then, he's basically been here at HKUST, and he works on atomic physics and has a lab that leads atomic quantum simulators. And today he is here to talk to us about quantum simulation with light, with atoms and light for scientific discovery. So please take it away. I believe the talk is for 1 hour, including questions.
Okay, thanks for the very generous introductions. So my name is Gyu Boong Jo from HKUST in Hong Kong. So I'd like to thank all the organizers for putting together all these great talks in this online conference. So today I would like to introduce our recent experimental works with the atoms and obviously lights, and in which we actually try to understand some property of the materials, and in general, I would like to emphasize how our quantum simulator works for these scientific discoveries. So today in this talk, I would like to discuss about, in general, about the quantum simulations. So the quantum simulation is quite a popular concept these days because in different platforms, such as the atom, molecules, ions, or even solid states device, we can actually emulate either the quantum circuit or quantum algorithm as shown in the right-hand side, or you can actually engineer the Hamiltonian of the system and you just let it go following the law of the nature. And in particular, you can simulate this Hamiltonian dynamics in these quantum simulators. Here, I just try to divide the quantum simulator into the two parts. One is the analog or specific quantum simulations. The other is so-called the digital type or universal quantum simulations. Well, in today's talk, I'll mainly focus on the left-hand side, which is so-called the analog quantum simulations, in which we do Hamiltonian engineering of the system, especially quantum system, and we try to understand how this Hamiltonian works. Likewise, the solid states reveal some property in a particular the material we are interested in. However, our group is also interested in this digital type quantum simulations. But for this job, we need to address the individual atoms or molecules, in general qubits, in a particular way, but we are not going to touch this digital type quantum simulator in these talks. So let me first focus on this analog version first. So our quantum resource is the atom. So you can imagine different kinds of atoms or molecules in general, but we are interested in the terbium atoms or erbium atoms in our group. So we basically start with the very hot atoms. So we heat up the atoms up to 500 Kelvin or even higher, and we generate the atomic beam, and eventually we cool down the atomic sample below very low temperature, typically 1 millikelvin or even lower. Once we follow these standard procedures, eventually you can cool down the atomic sample below the 100 nanokelvin. So why is that so cold? Because in that regime, the quantum mechanics is quite important, which means we are ready to do some quantum emulation or simulation with the quantum resources. Well, this is the snapshot of the lab at HKUST. So the top, I show this fermionic quantum simulators with the so-called ytterbium-173 atoms. So you see different color of the lasers, either this green or blue, because these ytterbium atoms requires several principal transitions, optical transitions, which is corresponding to the green lights or blue lights or even different color for different purpose. In the bottom, I show the snapshot of the other quantum simulator using the bosonic erbium atoms. So you see many laser lights and vacuum chambers and the optics for guiding the laser lights for manipulating the atoms. But if you may be wondering, where is the quantum simulators? And actually, the actual quantum simulation happens in the middle of the chambers. So here I show this schematic diagram of the vacuum chamber. So in the middle, we trap the ensemble of the atoms within the very tiny box of the trap. And the size of the trap is quite small, on the order of the 1 to 100 micrometer size. And once we trap those atoms in such a small box in the low temperature, you can start to design the Hamiltonian as we wish. So here I show the very typical Hamiltonian, or the system we design in the chamber. For instance, you shine the several different laser lights and generating the standing wave. Then those atoms start to see the periodic potential. We call it the optical lattices. And those atoms, the blue or red, that are corresponding to those different spins, behave like the electrons in the real solids. And this is the starting point of the quantum simulation for our experiments. Well, so the quantum simulation with ultracold atoms actually is very flexible. So you can imagine different kinds of the quantum simulations. For example, you can simulate how these particles reacts in this quantum chemistry. So you can emulate how the atoms and the other atoms merge together, forming the molecules. And this is the one type of the quantum simulation we can imagine. Other type of quantum simulation include the cosmology or particle physics, such as the collisions in the accelerators, or some dynamics in the early universe. You can also simulate using the ultracold atoms. If you simulate something or optimize something in a controlled way, you can actually do the quantum computation, which is the digital version of this quantum simulation, as I explained in the first slides of my talk. But today, I will rather focus on these quantum materials, which means what I mean by here is we can prepare the Hamiltonian, which is exactly the same as the Hamiltonian in the materials, and you can emulate how these electrons behave in the real solids using the ultracold atoms. And this is the main topic of my talk today. Well, so I'll give two example, very specific example using this atomic quantum simulators. So basically, we synthesize the quantum matter, and the first example is the topological matter. So to make the material topological, we need a different ingredients, but we'll focus on this synthetic spin-orbit coupling for the atomic systems. And I'll very briefly explain what kind of the band structure we can generate using this synthetic spin-orbit coupling. Then I'll mainly focus on these parts. So once we have this synthetic spin-orbit coupling, we have different kinds of topological materials. Then what if we introduce the dissipation into the system? So this is the deeply related to the talk given yesterday. So this is basically the topological materials in open quantum systems. So I'll mainly focus on these parts, and then I'll switch the gear to discuss different kinds of the quantum matter, so-called the Fermi liquid with SUN spin symmetry. So by the end of the talk, I would like to convince all of you that this atomic quantum simulator is very flexible to study different kinds of the quantum matter, as I give the two very specific examples. So let's start the first materials. So for the first materials, we are interested in the topological phase of matter. So many of us knows very well how we classify the materials following this traditional way. So if you look at this, for example, the magnetic materials, whenever this symmetry becomes broken, then we can classify the phase of matters across this phase transitions. But on the other hand, in recent years, people start to realize after this quantum Hall effects was found a long time ago, there's a different way to classify the materials based on this topology of the materials. So what I mean by here is we are not classifying the materials as we see, but if you look at this momentum space or block space, you can actually classify the topological property of the block space based on the eigenfunction of the materials in a different geometry or different coupling. You can classify the materials. And the famous example is the topological insulator, for instance, which was being actively studied in various systems. And this is what we are interested in this quantum simulations. In an atomic system for ultracold atoms, there is a different approach to make the system topological. Here, I just briefly summarize 3 different ways, which is basically the universal way even in the condensed matter systems. The first one is you can simply apply the uniform B field for the atoms in the periodic potential. So here I put the red atoms in the synthetic crystal or optical lattices. So if you apply the uniform B fields, because the length scale, there are 2 length scales competing with each other. First one is the lattice constant. The other one is the length scale set by the cyclotron motions in the presence of the B fields. If they compete, you expect this so-called butterfly spectrum, and you can get into this topological regime as long as you have a strong magnetic field. Another approach is to apply this local B fields in a staggered manner in a particular lattice type. Here I describe the so-called Haldane model in the graphene type lattice. So if you have this kind of staggered magnetic fields with a particular tunneling mechanism, you can make your system topological, or you can make your band structure in the block space topological. Then you can get into this topological system. The third way that we are going to focus on today is the spin-orbit coupling. So what I mean by here is instead of the spin polarized atoms or electrons into your system, you can imagine the spin up and spin down atoms or electrons in the lattice structure, and you can couple these 2 spins into the momentum. Simply saying, the spin-orbit coupling is the momentum of the particle is locked to the spin in a velocity-sensitive way or Doppler-sensitive way, and this is one of the typical mechanisms behind this topological insulator in the solid-state materials. So all those mechanisms have been actively studied and realized even in the atomic systems. And here I just group this atomic topological matter based on the technique people typically use. So the first one is the flow cat engineering, which is how this Haldane model has been realized in the graphene type lattice. So here in some lattice, people can apply this flow cat engineering by shaking the lattice structures, and they can couple the neighboring sides or next neighboring sides in a controlled manner. Another way is the Rydberg atoms, which is actively pushed these days. And today's talk will mainly focus on this Raman coupling technique, in which we actually use the 2 photon transitions with the 2 laser lights, and we couple spin up or spin down atoms as shown in this graph. And this Raman coupling method is quite popular in engineering this band structure for the ultracold atoms. However, let me emphasize one thing. So there are different kinds of atomic topological matter so far, but most of the realization so far was in the Hermitian Hamiltonian. What I mean by here is most of the realization isolate the system itself from the environment, and the system is well described by the Hermitian Hamiltonian without the dissipations, which is great because Hamiltonian can describe the system pretty well by ignoring any dissipation, any imperfections. But on the other hand, later I'll focus how we generalize this realization into the dissipative regime. Well, in our lab, we focus on the third method with the spin-orbit coupling. And the spin-orbit coupling, if you look at the Hamiltonians, the spin half atoms actually fills this synthetic magnetic fields. One thing I haven't mentioned about our neutral atoms, because we use the neutral atoms in our atomic quantum simulators, the atom does not feel this the magnetic fields. So what I mean by here is the real electrons actually has the cyclotron motion in the presence of the magnetic fields, the external magnetic fields, but our neutral atoms is charge neutral, so it doesn't feel any the Lorentz force in the presence of the magnetic fields. So we need to actually synthesize the artificial magnetic fields. For this, we actually we have to manipulate the vector potential A, then we can generate the synthetic magnetic fields. We do the same thing for the spin-orbit coupling. In this regard, the spin-orbit coupling is basically the generation of this vector potential A in a spin-sensitive way. So if you want to have just synthetic magnetic fields, you just control this vector potential A, but you don't need any spin-sensitive way. But as long as you introduce this spin-sensitive spin degrees of freedom into this vector potential, your system basically fills this spin-orbit coupling. In other words, your spin is locked to the momentum of your system. Well, there are different kinds of realizations, but one of the common way that we actually take in our lab is to use this Raman transitions between the spin up and spin down atoms. So in this schematic, the G1 and G2 represent the spin up and spin down atoms. And this is a very typical 3-level system coupled to the other with each other. And we basically shine the 2 laser lights with a detuning and far detune from these intermediate states. And whenever we couple the spin up and spin down atoms, this is what happened in the dispersion relations. So spin up and spin down atoms represented by the blue and these orange atoms. Without this spin-orbit coupling, these 2 spins reveals exactly same dispersion relations. Here there's no lattice, so it's a free space dispersion relations. But whenever they couple in a momentum sensitive way, whenever they couple, there is a momentum shift that's because of this Raman coupling. The photon should be observed and emitted from the atoms, and there is a momentum kick through this 2-photon process. Then these 2 bands will be momentum kicks, but the bands won't be crossed because of this coupling between the spin up and spin down, and we open the band gap. And this is the typical process for the spin-orbit coupling, and this is the base ingredients for this spin-orbit coupling and also topological insulator in the lattice. And this one has been very well demonstrated in the bulk system, in atomic system, and using this method or other methods such as the Flocken engineering, over the past few years in the atomic system, different kinds of very pedagogical model have been well realized in different dimensions. Especially from our lab, we actually realized the one-dimensional symmetry protected topological bands for ultracold fermions using the spin-orbit coupling technique in the optical lattices. And more recently, we could realize 3-dimensional band structure, especially with the nodal line semi-metal type band structure for these ultracold atoms in 3D. But again, I want to emphasize that most of the efforts have been done in the Hermitian region without the dissipation, or precisely by ignoring all this dissipation in the systems. But let me ask one question. So far in the atomic, these quantum simulators with atoms, you can synthesize and create this atomic topological matter in different contexts. But you can ask yourself, what if we actually generalize our system, or if you include any dissipation into your topological matter? Well, in other words, we heavily rely on this spin-orbit coupling mechanism behind this topological matter. But unfortunately, this mechanism, spin-orbit coupling, is less known in an open quantum system. Okay, so this is the fundamental question we have, and we try to answer to these questions by implementing this spin-orbit coupling with the dissipation in the atomic systems. So what we've done is very simple. We actually create the spin-orbit coupling for the atoms, but at the same time, we turn on the dissipation in a controlled manner. And we actually study this non-Hermitian spin-orbit coupling and realize so-called parity-time symmetry breaking traditions in the system. And we also explore how this spin-orbit coupled band structure affected when we control in a dynamic sense. And this is what I'm going to present in next 15 or 20 minutes. So if you have any questions, just feel free to ask anytime. Any questions so far? Okay, so let me go first. So before we get into this non-Hermitian spin-orbit coupling, let me just review very simple Hamiltonians. So even for the spin-orbit coupling, basically we are talking about the two-level system. So here I just present very simple two-level system with the coupling parameter G, and the detuning, the energy difference between the ground state and excited state is delta. So the Hamiltonian will be 2 by 2 matrix, and the G is the off-diagonal terms, and I have the energy splitting half delta plus minus, positive and negative half delta. But what if we introduce the gain and loss? So here, instead of just loss, I just put the gain and loss, because as long as you gauge out the system, basically gain and loss should be equivalent to the just loss as long as you gauge out. So for the simplicity, I just add the gain for the excited states and I put the loss for the ground state. In the Hamiltonian, we have this imaginary number I times gamma and minus I gamma whenever you have this loss. And let's think about the eigenvalue. Eigenvalue should be square root G squared plus the energy splitting plus I gamma square. Very straightforward. But if you imagine what happened to your eigenvalues when you have a really, really large gamma. For the zero gamma, nothing is special. But if you keep on increasing the gamma, you realize the eigenvalues becomes complex, which is obvious. And of course, that means the complex energy bands, energy bands become the complex as well. So this consequence has lots of the issues in the topological system in this regards, because when you imagine these topological materials, especially in the periodic potentials, you can imagine this the block band structure. Here I just put the lowest energy bands, and you can imagine this.
I didn't catch that. Could you try again?
Sorry, my phone response. Excuse me. So in this case, if you imagine these two bands in the block space, I represent this spin texture or eigenfunction of these bands as the blue and the red colors. And there is some spin texture along this causal momentum, and the system should be the topological or topologically non-trivial with some band gap opens. And so far in this Hermitian regime, all these energy bands are real values and nothing is that weird. And we know we can classify these topological bands following different periodic tables, such as the famous tenfold classification of the gap systems. But what if you introduce the dissipation into the system, as I just showed in the previous slides? We know that whenever you have this dissipation in an open quantum system, the energy bands becomes complex. So we have to re-examine, such as the definition of the block bands or Burke-Edge correspondence, which is the key idea behind these topological phases. We have to re-examine how this concept can be generalized, or we have to modify this principle to understand the topological phases in the open quantum systems. So this is our basic motivations, and we actually try in our experiments to answer to these questions. Well, to do that, we need to cook up these topological bands in the non-Hermitian regime for cold atoms. But this problem has been quite extensively studied in a different kinds of systems, such as the photonic system. People already realize the non-Hermitian band structure in the photonic crystal. So in this experiments in 2015, they already realized this photonic crystal both in the Hermitian and non-Hermitian regime, and they show that the band structure of the system becomes very different because of the dissipations. And this is very natural to imagine, because whenever you have a dissipation, your physical property of the system becomes different. In other words, my dissipation in my open quantum system can alter the physical property of the photonic crystal or real solids or even atomic systems. And that's exactly what we want to detect. So in the usual spin-orbit coupling, as I shown before in the Hermitian regime, this is the typical band structure or typical energy dispersions. And if you turn on the dissipation into the non-Hermitian regime, this band structure might be changed. And at a certain point, this band gap might be closed. And this is the very special points, so-called exceptional points. And this is what we want to detect and study in the atomic quantum simulators. And this is the building block for this non-Hermitian topological bands, even in the optical lattices. So this non-Hermitian physics has been extensively explored in a different kinds of system, mostly in the classical systems. Because in the classical photonic system, the photon loss is very natural because the light propagates along some axis and we keep on losing any photons. And this dissipation is very natural and cannot be avoidable. And people actually use this knob as the control knob in the system and study this non-Hermitian physics. In the classical system, various very interesting phenomena have been realized, such as the topological energy transfer has been demonstrated in this non-Hermitian physics regime. And this is what we actually try to do in the quantum system as well. So in our quantum system, we can go back to this original proposal by the Carl Vander and his colleagues. Originally, the non-Hermitian quantum physics has been proposed with the parity-time symmetry. And these gentlemen actually realized that even though the system is non-Hermitian regime, the eigenvalue could be still real valued or meaningful if this parity-time symmetry is well respected. And this is exactly what we can realize in either classical systems or even in quantum systems. Maybe some of you are not familiar with this parity-time symmetry, so let me emphasize what it really means. Well, this is the first experiments that realize this parity-time symmetry non-Hermitian systems. What they do in their classical but optical systems, they actually introduce the gain and loss into the two modes. In the quantum mechanical sense, it's the two states, but in this particular experiments, I'll call it two modes, but it's same for the quantum system. So blue modes or red modes, I have the gain and loss at the beginning. And let's see what happens if you apply this parity and time reversal symmetry. With a parity symmetry, basically what I do here is with the same gain and loss, I just switch this blue and red modes. And this is what I show here in the middle. But if you apply the time reversal symmetry, the gain becomes the loss for this red mode, and the loss becomes the gain for the blue modes. So if you compare the first and third system, it's basically same. All we did is we just switched the position and basically the same. Basically, you have the same system. So as long as this quantum or any system, classical system, follow this parity time symmetry, and your system still reveal this, the real valued eigenvalues. And this is the key idea of the system. And that's the reason why the loss or the gain of the system is quite important way or easiest way to achieve this PT symmetric system. That's what we do here in our system. But in the open quantum system, we have to be a little bit careful, because what happened in the open quantum system, basically whenever you have the constant loss or controlled loss into the system, this is the one of the common way we can describe the system following this Lindblad master equations. So basically, whenever you keep on losing the atoms, we have to write down the system based on the density matrix. And this is the basically the master equation we have. And so far, the system is not just non-Hermitian Hamiltonian, because we have some random terms, which is called the quantum jump terms. So we have to follow every single particle in the system, how they jump from one state to the other because of the coupling into the environments. But there's one thing we can do. For example, as long as you ignore these quantum jump terms, these terms, you can actually observe the last term back to the Hamiltonian. So what I mean by here is, as long as you redefine your Hamiltonian in this way, your Hamiltonian itself becomes non-Hermitian, but the system can be effectively described by this non-Hermitian Hamiltonian within the Schrödinger pictures. So in this case, in a particular case, when you can ignore these quantum jump terms, my system still follow the Schrödinger equations with the non-Hermitian Hamiltonian. And of course, this non-Hermitian Hamiltonian follows this PT symmetry, the parity-time symmetry. Then we actually go back to this Carl Bander's proposal and explore what happens. And this is the basic ideas of this non-Hermitian Hamiltonian. Well, and this is how we realize this non-Hermitian Hamiltonians, as I just described. So this is the basic idea of the spin-orbit couplings. As I explained before, we have a spin down and spin up atoms. In the real experiments, you can resolve the atoms with different spins. So here, blue and red spin represent the spin down and spin up atoms. So you can resolve all this spin information in the system. And the Hamiltonian is quite similar to the 2x2 matrix I explained in the beginning of this section. So, but we have a coupling omega r between these two states. We have energy splitting half delta. But one difference is the other terms in the diagonal terms is momentum sensitive. And that's the key idea of this spin-orbit coupling, because the momentum has to be coupled to the spin in a velocity sensitive way. So this Hamiltonian is quite similar to the 2x2 matrix with dissipation, 2x2 matrix without the dissipation. Then what we do here is we introduce the dissipation into the system. Well, you may realize that we have both negative sign for both spin up and spin down, which means I have a loss for the spin up and loss for the spin down as well. We have no gain. And if you look back the slides, I explained we had a gain and loss to have this PT symmetry. But in our case, we have just loss for the spin up and spin down atoms. But that's not a big problem, because as long as you gauge out the system, this differential loss, especially for our case, we have very small loss for the spin up and very large loss for the spin down atoms. And as long as you gauge out, you can recover this gain and loss in the system. For example, if you gauge out 7, I mean 7 out of this -13 and -1, you can have effectively +6 and -6, which is corresponding to the gain and loss of the system. So we have only spin sensitive loss in this spin-orbit coupled system. Then you have effectively the gain and loss in this spin-orbit coupled system. And let's see what the consequence is. So basically, you can calculate the band structure or energy dispersion in the presence of this dissipations. So here we represent very typical dispersion relations in the presence of this spin-orbit coupling without the dissipation. And now I turn on the dissipation horizontally. So then I turn on the dissipation a bit, and this gap becomes smaller. And at certain points, this energy gap is just closed. And if we go further, this band structure becomes just two free space dispersion relations. And this is one of the consequences. And it's because of the competition between the spin-orbit coupling and the dissipation of the systems. Well, we can resolve this band structure as a function of dissipation. So what we do is we put the atoms into these bands and monitor how this spin flip as a function of time. So without any dissipation, the bands, because of the energy bands gap, this Rabi spectroscopy tells us about the energy difference between the two bands, which is why we have these oscillations. If you increase the dissipation, this oscillation becomes less pronounced. At certain points, you close the gap between these two bands, and we do not have the clear oscillation anymore. So based on this band spectroscopy, you can reconstruct this band structure based on this momentum resolved the spectroscopy. So here I represent the response of this band structure as a function of the dissipation. So for first 300 microseconds, which is the vertical axis of each column map, we actually check how the spin flip itself as a function of the whole time. So based on this spectroscopy signal, you can map this phase diagram. So on the right-hand side, we actually represent the real valued energy gap and the imaginary part of the band gap. So they are corresponding to the band gap and the damping rates. And on the horizontal axis, we control this dissipations. So if you increase the dissipations, this band gap decrease and keep on decreasing until to the 0 points. But on the other hand, this damping rate is more like very small without big damping rates. And the left-hand side, we monitor the spin polarizations. So basically, the system goes between this up spin and down spin in a more like a symmetric way. But if you cross the very special points, the system get into a very different phase. It's called the parity-time broken states. And whenever you cross the line, the system behave in a very different way. For example, the band gap is completely closed, so there is no more finite band gap. But on the other hand, the damping rate increase rapidly. So in this PT broken states, the system does not oscillate between the 1 and -1 or between the spin up and spin down state anymore. It just monotonically goes to the some spin polarizations. So this PT symmetric versus PT broken states happens around this so-called very special points, and this point is called the exceptional point. So the exceptional point is very peculiar in the sense that when you control these dissipations at the exceptional points, both eigenvalue and eigenvector, they all merge, and it's very different from this Hermitian Hamiltonian. So to look at what happened around these exceptional points, we can go back to this energy diagrams. So as a function of dissipations, we have this momentum, the causing momentum Qx and the energy. And this parameter space can be dynamically tuned in our atomic quantum simulators. So what I mean by here is because we can control everything in a dynamic way, I can first prepare the system and rotate the system around these exceptional points. At the exceptional point, remember, the band gap is just closed. So I just indicate this exceptional points with this red cross. So you can just go around this exceptional point. You can encircle the exceptional point and see what happened in the system. But what's interesting around this exceptional point is the response of the system around the exceptional points depends on the chirality of the system. So first, you can encircle this exceptional points in a counterclockwise, but you can simultaneously test in the opposite way. You can encircle the exceptional point in the clockwise. So we can test how the system responds, and this is how the system responds. So for example, you can encircle the exceptional point either clockwise or counterclockwise, and we set the initial states, quantum states, same for both cases. So in the left-hand side, we start from this blue dashed line in terms of the spin polarization, and this is our initial quantum states. And we encircle the states, encircle the exceptional point either counterclockwise or clockwise. Surprisingly, if you encircle the exceptional point in the clockwise, the system is more like same as the initial states without spin flip. That's why the final states still represent the blue spins, but only for this counterclockwise encircling, the system flipped the spin to the red spins. So this response is very robust, and it also it only depends on the chirality of the system, either clockwise or counterclockwise. And this is fully because of the topological nature of these exceptional points in this non-Hermitian system. Right. So this is the one thing we can do with this spin-orbit coupling, and we can ask one more challenging question. So what if we bring this non-Hermitian spin-orbit coupling into the lattice? Well, the experiment I just demonstrated is in the bulk, has been done in the bulk without the periodic potential. And if you look at these topological phases in the optical lattices or in the real solids, we need to add this lattice systems with the spin-orbit coupling. And here is what we did. So even with many theoretical proposals, it was very challenging to combine the spin-orbit coupling in the lattice with the dissipations. But what we can imagine what it will happen. So in the topological system in the lattice, without the dissipation, typical topological bands looks like this. And this is how we realize even in our lab by combining the spin-orbit coupling with optical lattices. And if you introduce the strong dissipations, so as we illustrated in the bulk, this band gap will be closed because of the strong competition between the dissipation and spin-orbit coupling. And the question is how we resolve this exceptional points or exceptional lines in the optical lattice systems. And here is what we are doing right now. So we apply the same thing in the optical lattice systems, and theoretically, in a particular topological lattice system, if you introduce the atom loss, we expect to have these exceptional lines or points showing up in the band structure. And theoretically, we expect the band gap will be closed and multiple points in the block space, which is shown as these white lines. And at the same time, this imaginary part of the band gap or decay rates will emerge beyond these exceptional points or exceptional lines in the block space. And we actually can resolve these things in the real experiments. This is a very preliminary observations. So for 3 different dissipation, theoretically, we start to expect to see this exceptional lines or points, which is indicated by this white line or dashed lines. And we have successfully observe this this behavior by looking this so-called the Rabi spectroscopy, even in the optical lattices. So this platform, we expect very promising way to realize so-called non-Hermitian skin effects, which is the one of the important phenomena we are looking for in this non-Hermitian lattice systems. Okay, so so far we've discussed the first example of the synthetic quantum matter using the spin-orbit coupling and the dissipation in the systems. So for the remaining 10 minutes, I will switch our gear to discuss another type of the quantum matter in our quantum simulators. Well, so far we discussed how we engineer these topological bands for ultracold atoms, and we mainly realize topological insulator like a band structure for cold atoms. But now let me step back and ask very fundamental questions. So how does our electronic system works? Well, to discuss that, we need to think of this quantum statistics. In our neutral atoms, we can realize either bosonic systems or fermionic system. And this is how we imagine this bosonic system in the trap or fermionic system in a trap. Well, fermions, of course, if you have a spin polarized fermions, this is how we pack up following this Pauli principle. But you can imagine very peculiar system. What if you have a different color of spins, fermionic atoms? Well, in that case, you can pack multiple fermions in the same states because they have a different spins. As long as the different fermions in different spin interacts identically following this so-called SUN symmetry, and this SUN fermions is very popular concept in theoretical condensed matter, but unfortunately, it's really difficult to realize this kind of SUN, generalized SUN fermions in the solid states. But in the atomic system, because of the very special property of the atoms, we can actually realize such kind of SUN Fermi gases, especially the terbium atoms or strontium atoms, which belongs to the alkali earth and alkali earth-like isotopes. Because of the strong decoupling between the nuclear spins and electronic spins, our system naturally reveals these SUN symmetric interactions. And here I just represent two extreme cases in our system. For the spin polarized gas, they don't interact because of the Pauli exclusion principle. But if you prepare 6 different components or 6 different spins or different colors, they all interact with each other, but they interact identically. And this is the key idea of the SUN fermions. But one thing we need to remember is because of this multi-component fermions, their interactions are enhanced by the spin multiplicity n. And this SUN interactions or SUN enhanced interactions is the one of the key mechanism behind this Fermi SUN Fermi gases or SUN Fermi liquids. Well, so as one example, let me just give very extreme cases. So what if we have the bosons and fermions in the SUN Fermi gases? Well, we know this. In the quantum statistics, the bosons and fermionic quantum statistics is very different, strictly different in some sense. However, in a particular case, we know that this quantum statistics can be blurred. And particularly, if you imagine this one-dimensional case, and if you put the series of bosons in the one-dimensional systems, because of these one-dimensional confinements, the boson cannot penetrate each other. And eventually, you can write down the wave function. Likewise, you write in for the fermions. And as long as all the thermodynamic property can be well described by these fermionic wave functions. So it's so-called the fermionizations in the 1D for the hardcore bosons. The similar thing can happen for this SUN fermions. So what I mean by here is, what if you have spin polarized fermions or 2-component fermions or 3-component fermions? What if you have a very large number of components in your fermionic systems? Well, the first thing you can imagine is because of these interactions between different spin states, this Pauli exclusion principle will become weaker and weaker. Still, there is a Pauli exclusion principle, but the consequence of this exclusion principle could be probably negligible as long as the number of components is really large. And this is so-called the bosonization of the system. And this idea has been tested in different contexts by measuring the collective modes in this SUN fermions, either in one-dimensional case or the two-dimensional case. So what they do, or we did, is by measuring this collective mode frequency as a function of the number of components, we show that this collective mode frequency saturate to some value, which is the consistent with this bosonization scenario in this system. However, we think still we have some open question about this bosonization process, because if you look at the three-dimensional case, it's really difficult and challenging to calculate all these thermodynamic properties because of this three-dimensional natures. And there is no rigorous confirmation, even theoretical side, because of the complexity in calculations. So all we have to do is we have to rely on these experiments or experimental confirmation by using this quantum simulation experiments. And to do that, we actually look at how this individual particle interact with other particles by measuring so-called tense contact. Especially in our dilute quantum gas, this tense contact proposed by Shina Tan a while ago actually govern all these thermodynamic properties. So as long as you can measure this tense contact as a function of the number of components, we can safely or rigorously say that this bosonization happens in this system. So that's what we did. So this is the experimental measurements. This is the real data we take from our atomic quantum simulators. So we have many atoms, like 50,000 atoms, and we basically take this snapshot of the density distribution in the momentum space, and we look at how these tense contact behave as a function of the number of components. So to extract that information, we actually look at the basically large momentum, which is around here, which is basically empty space. So this very tiny signal, to extract such kind of signal, we did lots of improvements, such as statistical fringe removal process or even machine learning analysis. And finally, you can measure this tense contact or a very small signal out of this empty space in our data. And finally, you can measure this tense contact as a function of the number of spin components. But before I show the data, let me briefly explain what happened here. So if you have a spin polarized gas, basically there is no contact because of the Pauli blocking. So total interaction is basically number of atom n naught times 0, because there is no other contact parts. If you have a two components, basically the interaction is proportional to the number of atoms square. If you have three components, it's basically n naught square times 2. So enhanced by the two counterparts. If you have n components, basically the total contact or interaction occurrence is proportional to n minus 1. So what you can see here is if you increase the number of components from 1 to n, it should be scaled as 1 minus n minus 1. It is proportional to the number of components. That's exactly what we can measure in this experiments. That's what we actually measure. So in the horizontal axis, we control the number of components in this SUN fermions. So from 1 to 6, and we measure this contact or number of interactions in this system, and it's linearly proportional, which is exactly n-1, and where the n is the spin multiplicity. And if you rescale this contact and compare with the bosonic limits, we actually find this contact as a function of the spin states approach to the bosonic limit, even with a 3 to 4 number of spins, which is quite surprising. And actually, in our case, in our experimental data, we verify that the system quickly approached to this bosonic limit, which suggests that our system start to bosonize itself into the bosonic limit, even with 6 spins, not like 100 spins in the systems. And this is actually very rigorous verification of the bosonization in this atomic quantum simulations. Well, I think I run out of the time, but I have just one more slide. So what can we do more with this very peculiar SUN fermions? So SUN fermions is very interesting topic for the theoretical consideration, but it has not been well studied in the experimental sites, just because there are not many experimental platforms that we can study. So with this SUN fermions, we can actually do more thermodynamic measurements. So here I just illustrate what kind of tuning knob we have in our systems. For example, if you tune this SUN or number of spin components, you can study you can directly measure the compressibility of the system. And eventually you can regenerate the Landau parameter, likewise the Landau Fermi liquid in this SUN Fermi liquids. We actually can measure this compressibility. Furthermore, you can measure this compressibility for different SUN fermions as a function of temperature. So here I illustrate how we measure this compressibility as a function of normalized Fermi temperature. And we see that different SUN Fermi gas show slightly different behavior for different temperature. More recently, we start to prepare the imbalanced SUN fermions. So for example, if you control the imbalance between spin polarized gas and the 2-component Fermi gas, this compressibility should change as we expected. And this imbalanced Fermi gas is another direction we can explore to study this thermodynamic property of the SUN Fermi liquid. So here I came to the last slide of my talk. So I'm really happy to share 2 very specific examples of the material that we can simulate using atomic system. First, we discussed how we realize these topological materials using spin-away coupling in the atomic systems. So we can generate different kinds of topological insulator or nodal semi-metal for atoms. And if you introduce the dissipation into the system, the property of the topological matter dramatically change itself. And you can study different kinds of the properties such as the chiral spin transfer in the system. In the second part of my talk, we highlights how we realize this Fermi liquid with SUN spin symmetry in the systems. We have not covered another topic with the dipolar interactions. We also have another machines with this very special type of atoms in which we can study some dipolar quantum physics, but I couldn't cover that topic today. So in the last slides, I'd like to thank my team at HKUST, including the Terbium lab and Erbium lab and the new lab with the programmable quantum simulations. And thank you for your attention.
Thank you very much for that fantastic talk. We're running slightly late, so I think we should take maybe 1 or 2 quick questions. Please feel free to unmute and ask the question if anyone has a. So I think as people are setting up, may I just ask a quick question. There's something in the chat. Okay. So the question that I have is, this was the thing that has come up. I think the intersection of your work with my recent interests are basically in that Lindblad formalism. So I have always been a little bit kind of surprised by non-Hermitian Hamiltonians when I see them in the literature, because I think of kind of the more formal and correct approach to take is the kind of Lindblad approach. And so I think what you were suggesting is basically that you were saying the imaginary part of the Lindbladian, you could just, we would think of as a Lamb shift term that, that would renormalize the Hamiltonian. That's where, that slide exactly. So could you, if you drop the jump terms, can you just reiterate the argument that you're making? Can I take any Lindblad equation and just think of it as a non-Hermitian Hamiltonian and just forget about trace preservation, or just do trace preservation later? Is that the argument that you're doing?
Yeah, actually, that's very important question. So in principle, unless you have a bosonic systems, or unless you have a single qubit or single atoms, you could not completely ignore these quantum jump terms, because this quantum jump term is very important for the long-term scale.
Yes.
So in the extreme case, if you focus on the very early stage, like very coherent dynamics, then you can probably ignore this quantum jump terms, which is what we are in our experiments. So intuitively, coherent quantum dynamics, yes, you can ignore this quantum jump terms. But this quantum jump term is very important for the long-term behavior, or if you have a many-body quantum states. Strictly speaking, our system formed the Fermi sea, many particle with fermions. So we cannot completely ignore this quantum jump terms. However, our system has the intrinsic dissipation, the relaxation into the system. So even though there's a quantum jump terms in our system, it quickly relaxed back to the other states. So effectively, still we are describing our system following this non-Hermitian Hamiltonian, but one of our future experiments may focus on the role of this quantum jump terms. So we cannot ignore, definitely, in our system.
I see. Okay. Are there any more questions from the participants?
Maybe something comes to my mind. Shai, can I go ahead?
Please.
So yeah, I mean, you could do this. You could ignore this jump term, but I think there's some issue of post-selection here, right? I mean, because you have to renormalize the ensemble to have unitarity in some sense. Isn't that correct?
Yes, that's also a very good question. So basically, our experiment is based on the post-selections, because the particle is left, so we have no way to do it. So there is a subtle issue in our experiments when we interpret our experiments, but as I just mentioned, that very luckily, our system has a very strong relaxation when we introduce these laws into the system. So still, even though we post-select the system, still we are safe to ignore these quantum jump terms. But if we can minimize the relaxation of our system, there is a chance to look at the role of these quantum jump terms even in our system, which is one of our future experiment we have in mind at the moment. In that case, yes, this post-selection versus other effects can be further investigated.
Yeah, because usually what we found is that whenever the things are very interesting and exotic, that is a place where the post-selected ensemble is really shrinking in size, and then you can theoretically go ahead and predict something, but experimentally it's always a challenge if the post-selected ensemble is really tiny.
Exactly. Yeah. So yeah.
And the other thing which comes to my mind is that there's a fundamental difference when you write a non-Hermitian Hamiltonian. In a sense, the map you have is an invertible map, because in time when you're progressing, you can invert the map and go back in time. But this is exactly what a Lindbladian does not allow you to do, because it's not an invertible map. So there's a fundamental difference between the two. Oops.
Yes, that's exactly the point, because as long as we follow this effective non-Hermitian Hamiltonian, everything is basically coherent in some sense. So it's a reversible. But our real system is not the case. So we are still approximate our system based on this coherent quantum dynamics. So we cannot say that our system is in equilibrium. We just focus on the initial part or coherent part at the beginning.
Thank you. Thank you.
Thank you very much. So let's move on just so that we're roughly on time. So let's once again thank Professor Jo for that wonderful talk.
Thank you.
Thank you very much. And can I ask if Arul is here already?
Yeah, I'm here.
Hi, Arul. Yeah, please set up. Yeah. So we're running roughly 10 minutes late. So let me just quickly introduce Professor Arul Lakshminarayanan as he sets up. So again, it's a great pleasure to introduce Arul. He's my teacher. And so as a quick introduction for those who don't know him,